Okay, so very warm welcome to the students who are attending this pre-internship workshop. My name is Paris Palkar. I am the research assistant serving in the CFD Open team of FOSSEE, IIT Bombay. And the today's agenda is to demonstrate a heat transfer case study based on matrix cooling for gas turbine blades. So I would just like to thank Pranay for his demonstration on aerodynamic case studies. Now we will be moving towards heat transfer. The basic fluid is similar, but in heat transfer, our focus of interest is morely towards calculating the forces that are involved externally. For example, lift force, drag force, or we can calculate non-dimensional number such as coefficient of drag, coefficient of lift. However, in heat transfer, our main aim is to simulate conduction, convection, or radiation. These are the three modes of transfer, and we can plot some non-dimensional number such as Prandtl number, Nusselt number, etc., etc. Uh, Moving forward, so firstly, where you can find this case. So I'm linking this case website. You can just click on this website. It will directly make you to the FOSSEE's web page, where you can copy this matrix cooling for gas turbine blade. It is proposed by Mr. Jinu Chandra. Either you can download the abstract or you can download the whole case study to reproduce the results in your own system. Just to get a feel what we are doing, if you want to just understand what is being done, you can download the abstract. If you want to simulate everything from scratch, you can download the case study. A zip file will be downloaded in your system. You can extract it and make some changes as per your need. Okay, so this case study was proposed by Professor Himani Girl. She is the assistant professor at the University of Sweden. Along with that, Mr. Nikhil Chitnavis, who is a PhD scholar at IIT Madras and also a FOSSEE research associate, has contributed to this case. And they were working with Mr. Jinu Chandran, who is a research assistant at BITS Pilani. Our main objective of today's heat transfer case is to find the heat transfer characteristic with lattice work cooling structure operating in a turning flow configuration. So now you might be wondering what is a lattice cooling structure or why we are concerned about turning cooling structure. So previously, majorly the studies were carried out for the straight channel studies. Basically, lattice cooling configuration or straight lattice cooling configuration is used to trailing edge cooling application in gas turbines. The application domain is in gas turbines, nuclear system, or electronics, and here you can see there is a crisscross system arranged in a way so that the coolant can flow upwards and downwards. Here you can see there are two streams. This black border you can call it as sidewall, and the upper sub channel and lower sub channel consist of make a way through which the coolant flows, and with the combination of these two channels a rib is formed. And here you can see the straight channel and how we can simulate straight channel at various angle. So right now the inlet flow angle is 136 degree and the outlet flow angle is 68 degree. Similarly, you can change the angle of attack and angle of incidence to optimize the heat transfer area and get the results done. Simulating with all run. So if you are a newbie to OpenFOAM, you don't know anything about OpenFOAM, all you can do is download the case file. There is a, let me show you through my terminal. So if you download the zip file, here I have just simulated 3 cases, but you will be getting 5 cases. So what you can do is ls is just list out what is in the turbine cooling folder. Just list out what is in turbine cooling method. If I want to go in the case 1 folder, what I'll do is I'll do cd case, and if you hit tab, it will all on its own prompt you that the thing that you are interested in. So now I am in case 1. Now again I list out what is there in case 1. So there are various files that are present in this case one. Let us understand one by one what are them. Uh, Initially, if you don't know anything, you can directly open the README file. Here it is written to give executable permissions. You can run the script, all run and all clean. To run the full simulation, you need to use this command. And to clean the simulation, to remove all the working directories, you have to run the all clean command. So let us try them. Now I'll do the all run. So like I have used the all run script. So the first step was echo running block mesh and run application block mesh. So block mesh is a type of OpenFOAM utility that will create the background mesh for our snappy hex mesh, and to simulate our fluid problem. We can visualize it as well in the paraview part. I'll show it to you. I'll show that to you in some time. Next step is to run the surface feature extract. So what surface feature extract does is, if you are developing your own geometry in some another CAD modeling software, let's say FreeCAD or CATIA or anything, if you're using ANSYS Fluent, Space Clean, etc. So what you can do is you can directly export the .stl files, and you can directly place them into the try surface folder of your OpenFOAM OpenFOAM folder. Then what you can do is run the surface feature extract, and then OpenFOAM will try to capture the emesh file that are present here. It will try to capture the emesh file that are readable by OpenFOAM, and through which we can do our further refinement using Snappy Mesh and run our keys. Then the third thing is Snappy Mesh override. Snappy Mesh is a very complicated meshing directory. Again, it is provided by OpenFOAM itself. And the override command here states that key, whatever you have done previously in your Snappy Mesh, just rewrite it again. Anything for our application, running the Snappy Mesh could nearly take around for 1 to 2 hours. So I'm skipping that part. I have generated the mesh previously, so I'll show you using my presentation. Again, then there is an application called create patch override. Again, this override command is for the application, that whatever you have written in the create patch command, erase it and write it again. And for create patch, we are using our custom patches. Let's say if you are naming your inlet in CAD modeling software, so this will capture it and it will name it inlet in the OpenFOAM. Check mesh is a application in which you can check the mesh, how good your mesh is, how well structured your mesh is. Let's try check mesh. Check mesh works here. As we are not working with this case, I'll run just check mesh. Now this will run. Uh, just for your information, this is a very coarser mesh. The cell elements are near around 2.1 million, that is 21 lakhs, 91% of which are hexahedral, and the skewness index is near around 60%. That might cause some troubles in the that might convergence in future. So here you can see the total number of cells is 21,45,465. Okay. And if you want to visualize it, what you can do is there is an inbuilt utility provided by the ESI version, check mesh, right? If you write, then this will give you some information key what you can do. Just hit tab, it will give you further information about it. So I'll just write all fields. Now it will write everything from scratch, so that you can visualize it in your paraview. It is happening, just a minute. Now this is writing non-orthogonality angle, phase interpolation, phase skewness, and everything will be written into a file in your paraview. it has ended. Now the check mesh command has already executed successfully. Now what we have to do is we have to run our solver. For that, we will move further and I'll tell you how to run that as well. This is the all green script. If you want to delete everything like what we have run previously, let's say the check mesh or snappy x mesh or block mesh, if you want to erase everything from scratch, you can just do all clean and it will clean everything that was existing in your folder. There are steps what is being executed one by one. If you write back dot forward slash all clean, first it will remove all the time directories that were present. Then it will remove the mesh. Then it will remove the log files. Then it will remove the post processing folders. And then it will remove the e-meshes that were provided by Surface Feature Extract. While running the all run and all clean script, you can see a somehow similar window. Uh, Running this would nearly take around 8 hours. It took me 8 hours to simulate this. So I've just given you an idea what you should expect when you are running this case. So now we are moving towards the turning flow configuration. This geometry is proposed by Professor Himani, and this is used for trailing edge cooling application. And this is the inlet, and these are our ribs that we have discussed earlier. So when fluid enters from this inlet, it goes significant directional changes before going into the lattice work region. So you might be now wondering what is the lattice work region? Lattice work region is the region where upper stream and lower stream ribs are connected. So if you are able to see this section, it is known as the lattice work region. So this is the geometry and mesh discussion that we will be doing further. This is our inlet. This is a velocity type inlet. This is the lattice work region. If you are able to see, these are walls. Note that these are adiabatic walls, meaning there is no heat transfer occurring, and this is a pressure based outlet. Okay. The rim has a thickness of 4 mm. The height of rib is 10 mm. The inlet hydraulic diameter is near around 10 mm. The lattice section, that is this, it is around 265 into 85 mm. The beta angle is the angle of incidence that is occurring with the wall. This angle is 35 degree, and there are the channels are experiencing two angles in the inlet velocity. I'll show you what are those. For the downward angle, the angle is 145, and for the upward flow, the angle is 135. So let me show you. If you are able to see, there is a fine line that is separating our upper channel with lower channel. So the upward channel is facing the flow at the angle of 35 degree, whereas the downward channel is facing the flow at the angle of 145 degree. Now come towards the meshing part. Mind you, this is a very coarser mesh. I'm repeating this again and again because the grid independent study have not been carried out as of now. We can see the surface. This is the mesh, what it looks like. And if you want to see how the internal meshing is done, you can just go on this command. It is called slice on the upper ribbon, upper left ribbon. You can take a slice in the Z normal direction, that is normal to your flow, and you can hit apply. I have already that. It will take computational power, so I'm avoiding it. You can use solid color and you can use surface with edges so that it demonstrates you how the boundary layers have been formed here. So you can just twinklet it and see it very deeper way. So this is the boundary layers that are being formed, and this is the near view of the ribs. The total mesh count is 2.1 million, and out of which 91% of these cells are hexagonal. These are some boundary conditions that we are using for the simulation. For velocity, we are using fixed value, zero gradient, and for outlet. and for valves we are using no slip. If you want to know more about this, you can directly go to our spoken tutorials website. You can find everything about this, why this boundary condition is used for particular case in detail in those tutorials. I'll skip that due to time constraints. Turbulence modeling. In turbulence modeling, we are going with the SST K omega turbulence model to resolve the near wall behavior of the fluid and to capture accurate vortex structure. A dedicated turbulence modeling demonstration tutorial is in the line that will be provided by our FOSSEE research assistant. So kindly stay tuned for that. For now, we are using the buoyant bossing simple foam. It is used for steady and incompressible flow solver. And buoyant bossing simple foam generally works on the bossing approximation to model the density changes that arise due to the temperature. And this solver solves continuity, energy, and momentum. Only there is one thing that in momentum equation, a body forcing term is introduced to calculate the bossing approximation. It is generally used to simulate natural or forced convection in your CFD simulation. So now let's go to the results and discussion. This is the temperature plot for mass flow rate of 0.0139 kgs per second. And you can see the temperature distribution in this. This is for another parameter that is 0.0404 kg per second. For this plot, I have extracted the temperature plot as well as the velocity plot. This is taken from the upper stream of the view. So the angle of attack with the fluid was 35 degree. This is the temperature plot and this is the velocity plot. Now let's come to basic results and discussion. So here we can see that the pressure loss is increasing in the lattice work region as we increase the mass flow rate, and the change in pressure shows a non-linear trend for Reynolds number that indicates we are having some viscous losses and flow separation occurring near boundaries with higher velocities. Also, this is a coarser mesh, and if we refine our mesh more further and further, we will tend to get same physical results with more accuracy. And this is Nusselt number that has been plotted, and again the Nusselt number is also increasing as we increase the mass flow rate, and the increment is not uniform in both channel upstream and downstream, upward section and downward section. As for the upper sub channel, the flow is showing more chaotic in nature, and it is not aligned with the flow. You can plot your results in this. You can take a slice, then you can go on the temperature parameter and turn on the surface. So this is for 100 second. This simulation has been carried out for 1000 second, and this is what temperature contour looks at for time is equal to 100 seconds. Similarly, you can simulate you can visualize velocity as well. For again, this is for t is equal to 100 second as well, and there are various factors, that is k, alpha t, nut, omega, pressure. Uh, in this region, from inlet, you can see there is a from legend you can see there is high pressure region and it is low pressure region. So as the time will progress till 1000, the air will go from the high pressure region to low pressure region, and the air or the pressure in this system will be neutralized. That's all from my end. Thank you.